P9 Track UAV Behavior by Harish, Aritra, and Pranav. This research aims at improving UAV-assisted USV navigation by introducing an active camera control on the UAV's vision system and tracking the USV. Visually assisted UAV-USV teams have been used extensively in search and rescue operations. In such assists, having USV in sight from the UAV's camera is a primary problem for the responder. There can be many instances where the USV gets out of camera view. In such cases, there is a demand for active control of the camera's pitch and yaw to keep the USV in view. Several research teams have worked on visual control of the camera to track a moving object. Most of the methods rely on torque control or need position feedback from the actuators. Using position feedback is not a good option as it draws more power for the added feedback sensing functionality. Our algorithm introduces an elliptical region of interest and calculates relative position of Emily with the center of the image. When Emily moves out of the ellipse, the algorithm generates pan and tilt signals to move the camera and bring Emily back in view. The signals generated are sent to the Photokite's ground station using serial communication. A Photokite Pro UAV with a gimbal-equipped GoPro camera was used. The X and Y values generated by Yarn's code was fed to the control algorithm. The generated signals are sent to the Photokite using a libserial C++ library. We tested the control algorithm in the lab on 2 different test arenas totaling 20 trials. The paths were marked on the ground and the test dummy was moved upon it. This video shows the control algorithm moving the pitch in yaw real time. You can see the Photokite being held at its tether by Dufek, and we used a red bag to track as Emily's dummy. This video here shows the footage from the control code's point of view. You can see the control code tracking the bag when it moves out of the elliptical region of interest. It is to be noted that the control code acts only when the object moves outside the region of interest and stays put when it is inside, thereby saving precious battery power and eliminates unnecessary camera movements. We introduce 3 metrics to evaluate the control code. The first metric is the normalized distance parameter of Emily with respect to the ellipse center. A value greater than 1 means Emily is outside the region of interest, and less than 1 infers it is inside. This plot shows the time instances Emily goes outside the region of interest and the control code swiftly moving the camera's pan and tilt to bring Emily inside the field of view. 2 other metrics taken for the 20 trials as shown are control energy and sensitivity, which is average of ratio of height to time in the previous graph, which also proves that the control does a very good job in tracking the object.